Assalamualaikum and good morning to panel of examiner and everyone. My name is Norizin Azira binti Rushidin. Today, I will talk about my poster presentation of research project 2 with the title Effect of Sodium Alginate and Calcium Carbonate in Synthesizing of Xerogel-based active fruit bunch via overdrying in adsorption of engine oil. I will proceed with my poster presentation. This is my poster presentation for this research project 2, which consists of abstract, objective methodology, results, and conclusion. Abstract section. This research focuses on the possibility of Xerogel-based EFB as unadsorbent on engine oil with effect of chemical, sodium alginate, and calcium carbonate. This research provides a comparison in terms of physical structure, adsorption capacity, and shrinkage percentage between the standard ratio Xerogel and varying parameter Xerogel. The problem that led to this research are the environment of pollution that caused by the spillage of oil into land, river, and ocean, the disposal EFB that affect the soil due to the high carbon and nitrogen content, and lastly is the inefficient and high-cost technology in separating the oil. The highest adsorption capacity for Xerogel EFB in this experiment is 0.69, whereas the lowest adsorption capacity is 0.11. As a result, Xerogel-based active fruit bunch is a viable adsorbent for engine oil. The objective for this research are to synthesize the Xerogel-based active fruit bunch EFB via overdrying with the effect of sodium alginate and calcium carbonate. Secondly, to characterize the result Xerogel by SEM, PET, FTIR, XRD, and TGA, and the adsorption of Xerogel-based EFB using engine oil. In the methodology section, it is divided into three sections, which are the preparation of EFB, preparation of Xerogel, and adsorption of engine oil. For the preparation of EFB, procedure are taken from Abdul Wahab with few modifications. The pellet shape active fruit bunch EFB were reduced by using ball milling and blend using a mixer. Then, the blended EFB was placed in a sieve tray. Proceed with the preparation of standard ratio of Xerogel EFB, where 0.5 gram of sodium alginate was dissolved in the 50 ml of distilled water with a constant stirring 600 rpm. Then, 0.15 gram of calcium carbonate was added into the solution until fully homogenized. Next, 0.5 gram of EFB was added into the solution for 10 minutes before adding 0.15 gram of GTL into the mixture for 30 seconds. Then, quickly pour the solution into the mold. The gel is cooled in the cooler for 24 hours to allow for gelation. After 24 hours, mass and volume of hydrogel were recorded. The steps are repeated for each parameter, which is sodium alginate and calcium carbonate, with different weight percent. The hydrogel then is placed in a universal oven with a constant temperature of 60 degrees Celsius for 24 hours to produce Xerogel. After 24 hours, the measurement of mass and volume of Xerogel are recorded. Next is the preparation of adsorption test based on the ASTM. The adsorbent was put into the beaker with a tweezer in a 15 ml of used engine oil for 15 minutes. Next, the adsorbent is taken by using a tweezer and placed at the top of the empty beaker using a net strainer and drained for 30 seconds. The adsorbent weight was calculated and recorded. The procedure was repeated 3 times to obtain the average value for comparison and more precise tests for later on. Now, we'll proceed to the next result section where we discuss on finding of synthesizing and performance of Xerogel-based EFB. This figure shows the physical structure of Xerogel with the effect of sodium alginate and calcium carbonate. The increasing of sodium alginate resulting in darker color of Xerogel and becoming more harder, which shows from figure 1a to figure 1c, while in figure 2 shows the effect of calcium carbonate to the physical structure of Xerogel by decreasing the amount of calcium carbonate, resulting in thinner, brittle structure and more transparent color from figure 2c to figure 2a. Alginate is an anionic compound which is capable of forming gels in the presence of Ce2 plus ion released from calcium carbonate with the presence of GDL, dissolved in the alginate solution by internal gelation method. This figure shows the effect of sodium alginate on adsorption capacity and percentage shrinkage. The increasing in the amount of sodium alginate will decrease the adsorption capacity and also the percent shrinkage. This is because increasing in alginate only improves the structure of adsorbent, but lowering the adsorption capacity and also percent shrinkage due to the increasing of pore size and pore volume, which based on the PET results. The decrease in alginate will result in increasing of adsorption capacity because of the effective cross-link information of gel with equivalent ratio of calcium carbonate and GDL. This result is similar to Raj-Mohan, which obtained decreasing of adsorption capacity and percent shrinkage when increasing the amount of alginate due to worse of stability structure. This figure shows the effect of calcium carbonate on percentage shrinkage and adsorption capacity of engine oil. It was observed that decreasing trend of adsorption capacity and percentage shrinkage as the amount of calcium carbonate increasing. According to Osberg, amount of calcium carbonate should not be in excess than alginate and GDL. This is because the increasing amount of calcium carbonate will affect the gelation process, thus decrease the percent shrinkage and adsorption capacity. Calcium carbonate is relying with the amount of GDL and alginate. GDL will help the release of calcium ion and cross-link with alginate for the gelation process. The decreasing in the amount of calcium carbonate will increasing the adsorption capacity due to the effective of internal gelation process. Next, I will explain on SEM result. SEM is used to characterize the porous material by analysis on the surface morphology. In this figure, show surface morphology of zero-gel-based EFB with various magnification range. In the first figure, it was observed that the surface area of raw EFB is rough and rigid, consists of a highly ordered arrangement of the fibril. The strands of EFB show some crack and formation of micropores that result from lignin removal and allow for adsorption of engine oil. While in the second figure, display the surface morphology of blank alginate zero gel that shows smooth surface and homogeneous structure. This blank alginate zero gel sample shows a flexible structure which are easily bent without a breaking that happen due to the diffusion of calcium ion by internal gelation. Figure 3 shows the XEFB with various magnification. It can be seen that many EFB fiber attached in unalginate are maintaining its shapes and consist of pore. The addition of EFB to alginate causes change in the microstructure of zero gel. According to Hidayu, the activated EFB carbon contribute to 90% micropore of the total pore volume and the presence of tiny mesopore. In figure 4, show the raw EFB, XEFB and blank alginate zero gel at magnification of 500x. This figure focuses on the production of XEFB using internal gelation process. In the A figure show the fibrous structure of EFB, while B figure show the flat surface and homogeneous structure, and figure C display a fibrous structure and smooth surface with the combination of raw EFB and blank alginate zero gel sample. This morphology of the XEFB can be concluded that they consist of aggregate of small fibrillar network which are interconnected into pore and has a brittle structure. Hence, the internal gelation and drying process are completed. This table shows the surface area, total pore volume, and pore size for all samples from BET analysis employed with nitrogen gas. It was observed that standard zero gel shows insignificant change of surface area, pore size, and pore volume, while blank alginate zero gel display a high BET surface area and pore volume by decreasing pore size than raw EFB. The standard zero gel has low surface area and high pore volume compared to other sample due to the gelation process. Next, regarding the effect of chemical use, the decreasing individually of sodium alginate and calcium carbonate resulting in the increasing significantly pore volume that lead to high absorption capacity. In conclusion, the quantity of chemical also influence the pore size, pore volume, and surface area that contribute to the absorption capacity value. The figure in the left side shows XRD pattern consists of raw EFB and zero-gel EFB. The peaks of both samples display the presence of cellulose type 1 and lignin structure. Besides, the raw EFB shows the presence of crystal cellular structure at the sharp peak 22.17 degree, which similar from previous study. The XRD pattern of XEFB show broad peak because of amorphous material due to the chemical used in internal gelation process, while figure on the right side show TGE curve to compare the thermal stability of the sample and is divided into few regions. The first region is at temperature 39 degrees Celsius to 50 degrees Celsius show raw EFB release high amount of moisture content compared to blank alginate and zero gel. The next region show the first degradation of blank alginate due to release high amount of volatile matter compared to other sample. This is due to alginate release high amount of hydroxyl group and alginate backbone was breaking along increasing in the temperature. While the third region shows the degradation of all samples occur at temperature of approximately 900 degrees Celsius. Next, figure on the left side was observed. The raw EFB shows the OH stretching that indicate the presence of phenol and alcohol, while zero-gel EFB show diminition of OH stretching because of mass loss happened during drying method. Zero-gel EFB display the presence of C double bond O stretching indicate the presence of hemicellulose and lignin after the internal gelation and drying process. Both of the sample display the CO stretching indicate as any hydroglucose chain, while figure on the right side show the OH stretching that exists in zero-gel does not appear in blank alginate. There are several peaks that appear in blank alginate spectrum that represent the presence of CH stretching, C double bond O vibration that indicate the presence of carboxylate ion, and CH bending. In conclusion, the main objective of this research, which are to characterize the zero-gel EFB and investigate the absorption of zero-gel EFB on engine oil, were successfully carried out. Zero-gel EFB is characterized by using SEM, FTIR, TGA, XRD, and PET. The morphology of zero-gel EFB consists of a fibrillar network and smooth surface due to the presence of alginate in the sample. By decreasing the amount of sodium alginate or calcium carbonate will increase the absorption capacity and the shrinkage percentage. Overall, the zero-gel EFB is capable of absorbing engine oil, thus it is a valid adsorbent. My recommendation for the next researcher who interested in furthering this study is to use a different parameter such as the effect of contact time between the engine oil and the adsorbent, and effect of temperature towards the absorption of zero-gel on engine oil. Besides, the drying method can use a supercritical drying or freeze drying instead of conventional oven. Last but not at least is the use of various engine oil on the absorption of zero-gel based EFB. I would like to express my special thanks of gratitude to my supervisor, Prof. Dr. Azil Bahari Alias, and our coordinator for research project who gave me the golden opportunity to this wonderful project on the effect of sodium alginate and calcium carbonate in synthesizing of zero-gel based EFB via overdrying on absorption of engine oil. I will also like to thank my parents and friends who helped me a lot in finishing this project within the limited time. I am really thankful to them. That's all from me. Thank you also to the examiner for evaluating my poster presentation. That's all from me. Thank you to the panel of examiner for evaluating my poster presentation. You may contact me for the Q&A session. Thank you.